AP Kasabi, Unit 6-14. Quick little sort of lesson, just a couple examples, and then also just a kind of review of the topics that will be on the test on the back. So first we'll do what's on the front. This was actually from yesterday's assignment. I just want to do a quick refresh of the different ways we could do it. Old school is sort of taking the approach of like, let's not use anything new. Let's just find the inverse function first. This is a lot of work, and sometimes you just can't do it. So you swap the x's to the y's and the y's with the x's, and then you got to solve for y. Now this one, to do that, you would have to complete the square, which is honestly not bad compared to some of the situations you could get yourself in. So it's going to be the middle term divided by 2 squared. What if you added one side, get added the other, and then it's all okay. And then if you factor this, you should get y plus 1/2 squared. So the whole point of that is to get a binomial squared. So then you can take the square root of both sides to get y by itself. Now it says that x has to be positive, so we have to go with y is positive on the inverse. The domain of the original becomes the range of the inverse function. So if you solve for y, you get the square root of x plus 1/4 minus 1/2. And so that is the inverse function. So then you're going to take the derivative of it. So you're going to want that to be seen as a 1/2 power, so 1/2, x plus 1/4, so negative 1/2, minus 1. That derivative goes away. We could clean it up, 1/2, square root of x plus 1/4. And then you're going to plug the value that you want the derivative. You wanted it at x equals 20. So you plug 20 in there, give a least common denominator, 4 times 4. So that gives you 1/2 square root of 81/4, which gives you 1/2 times 9/2, which gives you 1/9. And that is the answer. Too much work is one comment I have. And also, you're going to get into situations where you just can't do that work. You can't do the work. It's not even an option. So we have this new school approach that I would recommend always using. I'll show you a third one just as more of a novelty, kind of a hybrid. But the new school approach says, you know what? We know that the derivative of the inverse is just the derivative of the original flipped upside down. And finding the derivative of the original is way easier. And then we don't have to find the inverse at all, which might be ugly or just impossible. The hardest part about it is making sure you know what to plug in. The derivative of this is super easy. And plugging a number in is super easy, and flipping is super easy. You just got the hardest thing is plugging the right number in there. Do not plug x equals 20 because that is the x value on the inverse, which translates to a y value on the original, right? From that, you can plug it in and figure out what the x should be. So I'd move everything one side, factor it. Now we're getting multiple answers, but we want the positive one. So this is on the original function. That's the value you need to use. That's the hardest part right there, is just getting the right value, because the derivative of the original function is super easy. And plugging a number into it is not difficult. You just got to make sure you're plugging the right number in. And flipping it is pretty easy also. So this is going to be the derivative of the inverse at 20 is going to be 1/9. Same answer that we got before. Lot less work, lot cleaner work. So this is the way we want to do it. Okay, now I do have a sort of old/new hybrid approach. A little of both. A little finding the inverse, but a little kind of new tricky stuff. So we could, go ahead and find the inverse, but avoid some of the potentially gross or impossible situations. So we could just simply swap the x's and y's, but then not try and solve for y, and take the derivative implicitly. Derivative of x is 1, derivative of y squared is y to the first, times derivative of y, what's inside dy dx, plus dy dx. And this is what you're looking for. The one problem is that you need the y value on the inverse function. You have x equals 20 on the inverse, which translates to y equals 20 on the original, but we need the y value on the inverse. So what we can do is find the x value on the inverse, and then whatever that x value on the original, that should be the y value on the inverse. So we plug y equals 20 into the original equation for the original function. We solve it. You'll notice we're doing a lot of the same work on this as we did on the new school approach. We're going to go with the positive. That's on the inverse function, which means that's the y value on the inverse. So x equals 4 is on the original, translates to y equals 4 on the inverse. That's what you're going to plug in for y up there. And then solve for dy dx. I made a mistake somewhere. What did I do? Oh, there should be a 2 here. Should be a 2 there. 2 there. 8, 9y. 1/9. Same answer. Kind of an old / new. But this is your best option. Okay. Now, just not related to that, log differentiation is a method I introduced earlier this unit about using logs to help you, log rules to help you make derivatives easier. This derivative right here would be gross, horribly gross. It doesn't even have logs in it, but what we could do is introduce a log of any base. I think natural log makes sense here because I see an e to a power, so it's going to clean up a little better if I use natural log. You use regular log, and then the derivatives of natural logs are just cleaner too. So what we're going to do is we're going to use log rules to break it up. But we had to introduce a log to just even get one. So it's going to be natural log of e to the x minus natural log of x squared square root of sine 2x plus 7. So that's the first step. That gets rid of the quotient rule. You move this out in front, that's going to become 1. So now that's x. So I'm not doing derivatives yet. I'm just cleaning up minus natural log of x squared plus natural log of sine 2x plus 7 to the 1/2 power. Now, I had to put parentheses around this. So multiplication means you add them, but this is all being subtracted. So I got to put parentheses around the whole thing and distribute. So now I have x minus, I could bring the 2 out front, 2 natural log of x, minus, I could bring the 1/2 out in front, 1/2 natural log of sine 2x plus 7. So I think that's about as far as I can go, but that got rid of a lot of stuff. That got rid of quotient rule, that got rid of product rule, that got rid of some chain rules and some power rules. This is going to be a lot cleaner. So now when you take the derivative, you're doing it implicitly though. 1 over y dy dx. Really small implicit over here. Derivative of x is 1 minus 2 over x minus 1/2 1 over sine 2x plus 7 times derivative of what's inside, cosine 2x times derivative of what's inside that, times 2. These 2's cancel. I want to get the dy dx by itself, so I'm going to multiply both sides by y. But I don't want y as my final answer because this wasn't really supposed to be an implicit problem. I manipulated it. So we really should have all x's in the end. But here it's easy. You have an expression for y in terms of x's. So it's going to be e to the x over x squared square root of sine 2x plus 7 for the y. And then you have 1 minus 2 over x minus, you have a cosine that, yeah, I don't think we're going to be able to break that up. Cosine 2x over sine 2x plus 7. You can't make that cotangent because it's plus 7 here. So I think that looks pretty good. And I think that was a lot cleaner and a lot easier than the other option. So just something to keep in mind. You can use logs, take advantage of logs. Log rules break up logs when they show up, but sometimes you could even introduce them yourself. Now, for the test, I have a review on the back, sort of a note sheet, and so we could kind of fill it out here, all the things that are going to be on your test, which is going to count as your final, so it's going to be 150 points. You're going to make it a little more than normal. Now, we're going to have related rates. You're going to have 3 of them on your test on one section, 3 of them with multiple questions on each one. Some of the possible relationships that you might involve like Pythagorean theorem. Some examples could be like the sliding ladder problem, the lighthouse rock problem, the rowboat problem with the dock, the 2 cars problems, the train and the car problem. So we've had a lot of problems that have involved Pythagorean theorem, right triangles. Area volume, tons of area volume, geometric, shape within a shape. Either 3-dimensional shape or 2-dimensional shape. A cone leaking, a cone being filled. It could be a cone leaking into a cube, like one shape going into another shape. Cones themselves are special, and they involve similar triangles. So, and you want to get into all R or all H, depending on what you're being given, what you're looking for. Similar triangles just come up a ton, of course, on cones, but also we had the shadow problems, right? Person walking towards the light post, the trough problem had similar triangles on it. So some different things to think about. We're going to have log and exponential derivatives. So we did add some new derivatives. All the previous derivatives are still fair game. But the derivative e to the x is e to the x. It's its own derivative. We could build in like the chain rule and kind of write it in terms of u and be e to the u times du dx. Same rule, just kind of thinking that you're probably going to have an inner function. And remember to do the chain rule. B to the x is going to be itself, but then you also need a natural log of the base. And this rule comes from this rule, special case. If the base is e, natural log of e is 1 and goes away. Again, you could write it kind of more with the chain rule built in. B to the u du dx. We need natural log of b stuck in there. Yeah. Natural log of x is another new derivative. It's just 1 over x. With the chain rule built in, it'd be 1 over u du dx. And also log with any base. So log with any base is going to be 1 over what's inside with an extra natural log of the base in the bottom. And we could write that kind of more in terms with the chain rule with the inner function. 1 over u, natural log of b times du dx. So those are the new derivative rules. Inverse functions and their derivatives. So that's something that we were just talking about recently. So some basic things: if AB is on fx, then BA is on the inverse function. So all the x's and y's swap. So we switch x and y. They're also reflections across y equals. Graphically, they are the reflection of each other across the line y equals x. The big new thing is that the derivative of the inverse at some point b is going to be 1 over the derivative of the original function at some point a. It's not going to be the same. B. This is the easiest or hardest part. Easiest part to mess up is what you plug in before you flip it. Okay. This is where we did old school versus new school. And you really should be going with the new school approach. Sometimes you just have to. Okay, inverse trig derivatives. I haven't talked about yet necessarily, but I'll put them on here. So inverse, we're going to talk about these in another lesson. The derivative inverse tan is 1 over 1 plus u squared du dx. And the derivative of inverse sine is 1 over the square root of 1 minus u squared du dx. And the derivative of inverse cosine, so these are derivatives of inverses, but some new ones that we haven't learned before. So we're going to add these to our list. And this one's going to be negative 1 over the square root of 1 minus u squared du dx. And so these are very similar. They're the same things, but this one has a negative, no surprise. Cosine has a negative. But we're going to have to probably memorize these. I'll try and show you where they come from. But this is a huge portion of the test below here. Function analysis. So this is where we're picking apart graphs, equations, line checks, and identifying all kinds of special points and special intervals. So we have critical points. And the way you find critical points is by setting f prime equal to 0 or undefined. We have stationary points. They're a subset of critical points. They're just when f prime equals 0. We have inflection points. And that is when f double prime equals 0 or undefined and the concavity changes. Okay. RE is for relative extrema. All right, relative extrema. And relative extrema happen when f prime equals 0 undefined. So they happen at critical points. And the slope changes signs. So that's where we use first derivative test. AE, we could say for absolute extrema. And best thing to do is to use EVT to find absolute maxes and mins. And the candidates are critical points and endpoints. Zeros are just where a function equals 0. They call them the roots, so we call them the x-intercepts of graph. So those are all special points on the graph. Special intervals are figuring out where the function is increasing or decreasing. So they're increasing when f prime is positive, and they're decreasing when f prime is negative. And you use a line check usually to figure those out. Concave up and down, the concave up when the second derivative is positive, concave down when the second derivative is negative. And again, using line check is really helpful for that. Above or below the x-axis, we don't do that much. That's just where the y values are positive or the y values are negative. And you could also use a line check to do that, but that's probably not a very common question I can give you guys. Graphing f from f prime. These are rough sketches, right? you're asking yourself, where is it increasing or decreasing? Concave up or concave down, and we're drawing little like quarter circles, okay? And you got to start at some arbitrary value C. So we've done that. FDT, first derivative test for relative extrema. The basic idea, so you don't have to memorize this just without context, is to look at the derivative values, the slopes, and see what happens when they change. At a peak, f prime equals 0 or undefined. It could be a sharp peak. The slope goes from positive to negative, right? And at a valley, at a relative min, f prime equals 0, undefined. You're going down and then up. You got to be at the bottom of something if you're doing that. So f prime changes signs. More specifically, when f prime goes from positive to negative, you're going up and then down. You're at a relative max. When f prime goes from negative to positive, don't memorize this, just think about it. You're going down and up. That's a valley, that's a low point, that's a relative min. So that's the first derivative test. The second derivative test, we usually only use if we can't use the first derivative test because it's more work. And it says, well, you know you have a critical point and you know the concavity. So if it's concave down, f double prime is negative, and you have a critical point, f prime equals 0, then that's got to be a relative max, right? You can see it. It's a high point. If it's concave up and you have a critical point, f prime equals 0, then that's got to be a relative min. Look, that's a low point. So I wouldn't memorize those. I would just draw little pictures. So if you have a critical point and you know f double prime is positive, you're going to get a relative min. If you have a critical point and you know f double prime is negative, you're going to get a relative max. Don't memorize it. Think about it. Don't memorize these things. Picture them. Draw little sketches. Now, the critical points specifically have to be when f prime equals 0. It cannot be when they're undefined, because if the first derivative is undefined, the second derivative is going to be undefined, and there's no concavity there. EVT, extreme value theorem. There are some requirements of using this. The graph needs to be continuous and on a closed interval. So it's got to be all connected, no jump holes, vertical asymptotes. It's got to have endpoints. And the candidates for that might be the absolute max and min are going to happen at the critical points and the endpoints. Got to check the endpoints. And what we do is we just plug into the original to see what the values are. So we usually use a table and we plug them back into the original. And we plug the endpoints and all the critical points that we find that are between the endpoints. And from there, we find the biggest and smallest value. Now, these are the locations of the absolute max and mins. And these are the actual absolute max min values. The y values are the absolute max min values. Okay? Be prepared. But I mean, this is a ton of the test. Is this function analysis is what I call it. Looking at graphs, looking at the graph of the derivative, looking at equations, using line checks to figure out where all these special things are. Special points, relative maxes, mins, absolute maxes, mins, critical points, all that stuff. So, all right, that's it.